Hi, I am Adrián Pastine from Universidad Nacional de San Luis. I'm going to be talking about the diameter of Schrijver graphs. This is joint work with Pablo Torres from Universidad Nacional de Rosario and Mario Valencia-Pabon from Université Sorbonne Paris Nord. First, I need to define you Nisser graph, as I need them from the definition of Schrijver graph. So Nisser graphs are quite widely known. Given a base set of n elements, the Nisser graph on n and k has as vertices the k elements subset of that set, and two vertices are neighbors if they are disjoint. So here we have the base element of numbers from 1 through 5. 1, 2 is disjoint, is neighbors of 3, 4, 3, 5, and 4, 5 because they are disjoint. Now, we want to, for Schrijver graphs, we want to have the base set be a set of consecutive numbers, because what we're going to do is we're going to remove vertices that are cyclically consecutive, that have cyclically consecutive elements. So 1 and 2 are consecutive, we remove that. 3 and 4 consecutive, we remove that. And since 5 in this case is n, 5 and 1 are considered consecutive. That's what I mean with cyclically consecutive. So I remove that. I also remove 2, 3, and 4, 5 because they are consecutive. That is the Schrijver graph. Right, so keep in mind that we don't want to have consecutive elements. And next, for the diameter of graph, the distance between two vertices is the length of a shortest path between them, and the diameter of the graph is the longest distance amongst its vertices. So the two vertices that are the furthest apart give you the diameter of the graph. The theorem that we have, or the result that we prove, is that the diameter of SG to K plus RK is 2 if R is big enough, 3 if R is big but not so big, K if R is really small, and when R is between 2 and K minus 3, we have that the diameter is at least 4 and at most K minus R plus 1. So the rest of the talk is going to focus on trying to show you how to get this upper bound. The rest of these are quite easy. It's just that in this case the graph is a cycle, so it's trivial to find the diameter, and in these cases you have either enough places so that any pair of vertices have at least a neighbor in common, or at most 2 steps on the way. So I want to show you a little bit of how to think this. I think that this is going to make it easier to follow the rest of the talk. So here we have SG20, and here I have the 20 elements of the base set. I have vertices A and B. So here I'm coloring the elements of A with red and of B with blue. 8, 10, and 12 are colored purple because they are both in A and B. So typically what you want to do to prove the upper bound for diameter is, given any two vertices, find a path between them. So what we are going to try to do is find two vertices that are neighbors, one with A and the other with B, and such that the intersection between the vertices is less than the intersection between A and B. So notice that whatever it is in A but not in B, whatever is in B and not in A, we can put in A star, right? Because we want it to be disjoint with A. In the same way, whatever is in A and not in B, we can put in B star. Next, whatever is next to something in B star, we know that we are not going to use that in B star, so we can put that in A star, unless it is also next to something in A star. Right? This is because of that Schrijver non-consecutive thing condition. And next, whatever is in A star, next to something in A star, we can try to put that on B star. We can keep going that way until we have placed everything, except we haven't placed things that are between these purple elements. And now what we can do to complete A star is, notice that B star already has 7 elements. To complete A star, we can choose something from there and put it there. Right? So now we have A star and B star that are vertices, and that they are giving you that the distance between A and B is at most 3. Another thing that may happen is that if you have enough white squares, you can probably form an extra vertex, like this guy C here, that is neighbors with both A and B. Right? So those are the sort of two things that I want you to have in mind. So from that, we have some types of logs that depend on what are surrounding those blocks. So blocks of white squares, that's what I mean with blocks of consecutive white squares, and the type of the block depends on whether what is on the borders is in the intersection, just one of them in the intersection, or neither of them in the intersection. So with all of these type 2, 3, and 4, there are some technical lemmas that we did that I'm not going to show you, but they prove that A star and B star can be done of a nice enough size. And again, the construction is as we did before for A star and B star. Notice that with type 4H and type 4A and B, there may be some squares that we are not using, but type 2 and 3 we use everything. And then with type 1 we also use everything, and in most cases in those technical lemmas we show that we can use everything without intersection, unless they are this sort of things, short type 1, which is just one white square surrounded by purple. These are the guys where we are gonna get the intersection between A star and B star. And so the lemma that we prove that is sort of the key to everything is that if you have two sets that you have two sets A star and B star, so that A star is neighbors with A, B star is neighbors with B, and the intersection between A star and B star is at most the amount of short type 1 blocks. Using that, we know that the intersection between A star and B star is at most the intersection of A and B minus 1, because short type 1 is surrounded by intersections of A and B, and thus the distance between A and B is at most 1 plus 2 times the intersection, right? Because we just keep using this lemma repeatedly until you find A, P, and BP that are neighbors. And even more, if I is empty, then the distance between A and B is at most 3. Another corollary that I want to show you, because we're going to use it in the next slide as a tool, is that for any third vertex y, the distance between A and B is at most 2 plus 2 times the intersection of A and y plus the intersection between B and y. And finally, the other thing that we get is just counting a little bit of the places that you may have, is that the diameter of SG to k plus r k, when r is between k minus 2 and 2k minus 3, is at most 3. It's not exactly 3 from there. We also need to have an example of two vertices that are at distance 3, but I'm not going to show you that here. Okay, but these 3 corollaries we're going to use sort of in the next slide. So the strategy to bound k minus r plus 1 when r is between 2 and k minus 3, to bound with k minus r plus 1, sorry, is given two vertices A and B, what we're going to be doing is adding extra white elements in that array. So we sort of start raising these vertices to Schrijver graphs on a bigger number on a bigger base set without increasing k. We are going to be using two types of operations, and we are going to use them successively until we find AP and BP that are at distance at most 3 in SG2k plus r plus p. Because of that last corollary that I showed you that said that the diameter when r is k minus 2 is at most 3, we know that p is at most k minus 2 minus r. Well, I'm not exactly going to show you where this comes into play. I'm going to tell you though. Now, what may happen between AP and BP is that the distance is either 2 or 3. If the distance is 2, we're going to get a vertex y that has a small intersection with A and with B, and then use that corollary from before. And if the distance is 3, we get two new vertices, A star and B star, with a small intersection between them, such that A star is neighbors with A and B star is neighbors with B. So this condition on P is what is going to give you these two upper bounds here. So let me show you how this works. When the distance, so here I'm going to show you what will happen when the distance is 2. I'm using as an example SG157. So first what we do is we find a block of consecutive alternating color elements, so red, blue, red, blue, red, blue, and so on. And we add a white element between the second and the third elements in that block. So between second and third here we add a white element. we always start with that operation, that is the plus operation. Next, the up arrow operation, what it's going to do is it's going to add an extra element in a short type 1 block. So here we have a short type 1, we add an extra element. Now we want to go back to plus. It's always plus, up, and so on. So here we have these 4 consecutive elements. We want to add something between the second and the third. And once we did that, you may notice that we have this green vertex here that is neither adjacent to red nor adjacent to blue, or not disjoint from red and blue, and so that vertex is neighbors with AP and PP, and is giving you that the distance between them is 2. We are going to take that vertex and start going back from the operations. When we go back from the plus operation, we have to move this guy to the left, and that is giving us intersection between it and the blue vertex. But when we go back from the up arrow operation, we cannot be using these 2 guys in the green vertex, so we don't get any extra intersection there. Now we are gonna go back from the plus operation, and again we get intersection. So what happens is that the intersection between this green guy and the 2 previous and red and blue is at most the amount of plus operations that we did, and that gets bounded by P, and it gives you the upper bound that I showed you before. For the case when the distance ends up being 3, again we do the same thing, but now as distance is 3, what we found is an A star and B star that are disjoint. Now when we go up from the up arrow operation, what is going to happen is that in this block we are using A star and B star in the 2 elements, so this is giving us an intersection between A star and B star. When we go back from the plus operation, we don't get any intersection because this is one of those type 4 blocks. Notice that this is surrounded by A star and B star, so there is no way we can use it. So every up operation is giving you an intersection between them. Any plus operation is giving you no intersections at all. So the intersection between A star and B star is at most the amount of up operations that you did, and that is where that other bound comes from. So with all of that together, again, this is the result that we prove. And some things that remain to be shown are, well, we need to find better lower bounds when r is between 2 and k minus 3, because the lower bound that we found is 4, and yeah, that is good when r is close to k minus 3, but it's really bad when r is small. We want to either show that our upper bound is sharp, or find a better upper bound. And I think that it is sharp when r is big, when it's closer to k, but I think that when r is small, probably the upper bound could be improved. And then the last thing, that after finishing this is probably saying, okay, we want to actually find the actual diameter of those graphs. The next thing will be to study the diameter of S-stable Nisser graphs, which are obtained instead of deleting vertices that have consecutive elements, we delete vertices that have elements at cyclic distance less than or equal to S. Right, so those are some upper problems to study, and that is all. Thank you for your attention. Before we leave, I wanted to mention that this work was partially supported by LIA Infinite Sin Fin and by the Matamsud project. So thank you so much.